right? So I'm going to use this. But in section 3.2, we're going to derive some formulas. That make things a lot easier than using that definition. But in order to derive the formulas, I'll use the definition and establish some patterns. So firstly, remember that this derivative came from computing a slope. And so we interpret this as the slope of the tangent line to f at any x. And that's essentially the slope of the graph. It tells us how steep the graph is at a particular point. So using slope as our interpretation and f prime as our notation for the derivative, let's just look at some quickies here. What is the graph of f of x is equal to just a single number? What kind of graph does that have? 5. F of x is equal to 5. It's a horizontal line, isn't it? This is the graph of a horizontal line, or is a function whose graph is a horizontal line. So its derivative should represent the slope of a horizontal line. Can you tell me what the slope of a horizontal line is? It's 0. So my first derivative rule is that the derivative of a constant is equal to 0. So let's see, I'm gonna put that up here, maybe not. I'll put it over here. I'll do that. All right, so our first derivative rule is that the derivative with respect to x of any constant is equal to 0. Now that I need to show. Derivative of any constant is 0, no matter how funky the constant is. The derivative of 5 is 0. The derivative of a half is 0. The derivative of pi is 0. What's the graph of f of x is equal to x? Y is equal to x. What does that graph look like? It's a line that goes straight to the origin, right? What's the slope of that line? 1, the number in front of the x. So the derivative of this particular function is 1. That's our second rule. Derivative with respect to x of just a single variable x is 1. Or if I had the equation of any line up here, mx plus b, the derivative with respect to x of mx plus b, since that's a line with slope m, is always m. Now I'm going to derive the formula that tells us how to take the derivative with respect to x of x to any power. But I'm going to do that with a pattern. I'm going to take the derivative of x squared, of x cubed, of x to the 4th, and then I'm going to use this, and then we'll make a general rule, and then we'll try it over here. Okay, so let's do that. With my eraser. So for f of x is x squared, using this, f prime of x is the limit as h goes to 0. Now I have to take x plus h and put it right here and square it. Minus the function that's given, and then do the squaring. The squaring, eventually we'll be able to cancel that h. So remember, when you square x plus h, you'll get 3 terms. Do you know the 3 terms you'll get? What's the first term? There you go, keep going. Plus 2xh plus h squared, very good. The x squared in the front adds out with the x squared in the back. The terms that are left have a common factor of h. So I'm going to take an h out of each spot. So put it right over here. So I got h times 2x plus h over h. Cancel those h's. Take the limit as x goes to 0 of 2x plus h. H is going to 0, so this term is going to vanish, and we're left with 2x. Okay, so I'm going to put my pattern up here. Starting with the derivative of x to the first power being just 1. Derivative of x squared is 2x. So now we're just going to do this by erasing some stuff, because I'm going to build my powers up. I'm going to make this x cubed. So that's going to change these to 3, and then I'll rub the rest of this stuff out. So let's now make it x cubed. All that does is make that and that into a 3. But cubing this means take x plus h and multiply it with itself 3 times. But I'm going to do that using Pascal's triangle. Any of you ever been shown Pascal's triangle, used it in a previous life? The reincarnation type. Here's Pascal's triangle. I bet you've seen it. It's a 1. The next row has 2 1s that kind of surround that 1. And then a 1, 2, 1. And then 1, 3, 3, 1. And then 1, 4, 6, 4, 1. That bringing back any memories? So how am I getting the numbers in each row? Would you be able to write the next row? This 10 comes from adding the 2 numbers above it. This 10 is the sum of the 2 numbers above it. 4 plus 1 gives us 5. Those numbers are used in many applications, but one application is that these give us the coefficients of raising a binomial to a power. The first row is the coefficient of, say, a plus b to the 0 power. Any number to the 0 power is just 1. The second row is a plus b to the first power. You get 1a plus 1b. The third row tells us what a plus b cubed is, squared is. A plus b squared would have 1a squared plus 2ab plus b squared. Let me go. Is that better? Is that what you guys are asking about over here? No idea how to arrange this. All right, so there's old Pascal's triangle. Those off for a minute. I'll put them back on here. So this row should tell me what a plus b all cubed looks like. This row tells me that if I take two terms and raise them to the third power, like I'm going to do here, I should get 1 times that first number to the third power. The 3 is going to be the coefficient of the first number squared, go down by 1 power. But then put a b on there so that the total of the exponents adds to 3. The next term would have another 3 on it. And then you'll have an a to the first power and a b squared. And then a 1, a will now be to the 0 power and b will be to the third power. Pretty cool, huh? The powers on the first term start at the original exponent and go down by 1. And the powers on the second term start at 0 and go up by 1, so that any one term has exponents who add to the original power outside the binomial. And so x plus h all cubed is going to look like that. Each a is an x and each b is an h. So it's going to look like, there's our limit, x cubed plus 3 x squared h plus another 3 x to the first h squared plus a 1 times h cubed. Then from the formula, I've got the minus x cubed, and then I have divided by h. And as before, the x cubes add each other out. Everything else has an h in it. So I'm going to factor out an h and cancel it, but I'm going to kind of take a shortcut. I'm going to factor out 1h from each of these. And now I'm going to write what's left. I'm going to have a 3x squared, that h next to it is canceled, a 3xh, and then plus h squared. And I canceled the h on the bottom. Each h goes to 0 because I can now take the limit. So this term is going to be wiped out, and so is that one. And the next term in our pattern is that the derivative of x to the third power is 3x squared. And since we have Pascal's triangle up there, I'm going to use it to take the derivative of x to the fourth power. So let's put that in our pattern. I'm going to erase this because it got in my way. So you written that part down yet? I'm going to rub it out. Derivative with respect to x of x to the third power is 3x squared. So now we're going to make this x to the fourth power, which changes this to a 4 and that to a 4. And then we'll use Pascal's triangle and get a new line right here. So here's the line we're going to use for the fourth power. We'll have x to the fourth plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus 1h to the fourth. Say 4. I have an x squared h squared and 6. And then I have an x to the first, h to the third, and a 4. And no more x's. I just have a 1, h to the fourth. Have minus x to the fourth all over h. So here at the end, there at the front, we lose the x to the fourth. Everything else has an h in it. We're going to take 1 h out of each of those slots. So that one takes out 1 here. That's now h to the first. That's an h squared. That's an h cubed. I think I can put it right down here at the bottom so you in the back row can't see it. I've got 4x cubed plus 6x squared h plus 4xh squared plus h cubed left after I cancel the h. Canceling the h on the bottom allows me to take the limit. And so that one's going to be 0. That one's going to be 0. And that one's going to be 0. And we're left with 4x cubed as the derivative. So the derivative with respect to x of x to the fourth is 4x cubed. And so I think 4 terms here is enough to get us a smooth pattern. So the first thing I want you to notice is whatever power of the x is here, its derivative is 1 power less. Think of this constant as x to the 0. So the derivative is always 1 power less. Then what about the number that's in front of the x? Well, they count, right? They're counting with us 1, 2, 3, 4, but they're also matching whatever the power was. So the derivative of x to a positive power should look like whatever that power is, x to 1 power less. Agreed? So let's write that down. You should be able to put the power right here, 1 power less there. But I'm not sure if this works with negative powers, because I won't be able to use Pascal's triangle there. So what I want to do is I want to use this definition and take the derivative using x to the -1 and x to the -2. And then if we're happy with that, then we can see if this rule applies to negative powers. Okay, so now we're going to look at for f of x is equal to x to the -1. We're going to see if that rule holds for it. X to the -1 means 1 over x. According to the definition, f prime of x should be the limit as h goes to 0. We have to evaluate that when x is replaced by x plus h. And I'm going to do it in this form, 1 over x plus h. Then subtract the function as you see it, 1 over x. Then divide by h. So Pascal's triangle doesn't apply anymore. But instead, x to a negative power makes fractions. In order to subtract fractions, you need a common denominator. So I'm going to do that right here. I'm going to multiply the first fraction by the other fraction's denominator, and the second fraction by the first fraction's denominator. And so we have the limit as h goes to 0. I'm going to have 2 fractions that both have x times x plus h as the denominator. The first one will have x in the numerator. The second one has an x plus h in the numerator. Then we have to divide that by h. I put the second bit in parentheses because I have to subtract the entire x plus h. So now I'm going to take the parentheses off just with my eraser and distribute the minus sign. So that makes the first term that, and it's going to put a minus sign here. And that gets rid of the 2 x's on top. Those parentheses are in my way. So that adds out with that. And so we have the limit as h goes to 0. I have a minus h on top, the x times x plus h on the bottom, and then that's divided by h. To divide by h, I flip it over and make it a 1 over h and multiply. There's the step I needed to cancel that pesky h. And now we're going to take the limit as h goes to 0 of, well, h cancels, I better put a minus 1 here. And then I have x times x plus h. Make that h into a 0 now. And I have negative 1 over x squared. Or if I rewrite it so that it looks like this, I can write that as negative 1 x to the negative 2. And you tell me if this pattern holds for taking the derivative of x to the negative 1. Old exponent, the new exponent is 1 less. You like it? You convinced? So let's just generalize that that works for all positive integers, negative integers. Now let's look at if we have a fraction. So let's see if this rule holds, say if the exponent is a 1/2 power. So let's go back and make that a 1/2 power. And make that, remind you that that's the same as the square root of x. Then I'll write down the definition of the derivative for the square root of x. It's the limit as h goes to 0. We have to replace x with x plus h. So I have the square root of x plus h minus the square root of x, all divided by h. So again, that's not helpful anymore. Let's take Pascal's triangle out of here. But in order to get rid of the h that's giving us the 0 over 0 here, we've got to clean up the radicals from the numerator, and our trick there is to multiply by the conjugate. We multiply top and bottom by the numerator, but put a plus sign in there. I'll do it right here. Oops, over the same thing. I'll go backwards this time. I'll come back this way. Having the opposite sign in here gets rid of the middle terms. The middle terms come from this product and that product. Those are both the same, but opposite in sign. So you just end up with the first term squared minus the last term squared. The first term squared gets rid of the square root sign on the x plus h. Minus the last term squared is going to give me the square root of x squared, which is just x. See how that happened? Do too much in one step. So the x's add each other out. We got that h up there. And h down here that I left factored out because I knew that I was going to cancel it. And here I cancel it, and it leaves me just a 1 in the numerator. Once I cancel that h, I can replace that with 0. And we have 1 over the square root of x plus the square root of x, which is 1 over 2 square root of x. A square root sign is a 1/2 power. So this is same as 1 over 2 x to the 1/2. And if I move that x upstairs to see if it fits the pattern, then I have to change the sign on the exponent. So let's bring that over here and see if it fits the pattern. When the original exponent was a 1/2, bring the 1/2 down in front. Yep, it's there. The new exponent is 1 less than the original exponent. Do you agree that negative 1/2 is 1 less than 1/2? 1/2 minus 1 is -1/2. So if it worked for x to the 1/2, are you going to believe me that it works for x to the 1/3, x to the 5/9? This works for any power in the world. And for that reason, we'll call it the power rule. Okay. So now let's talk about when we have the sum of terms together. Let's see, the other day we took the derivative of a polynomial. I don't want to bring that up yet. Let me just talk about, we got 2 more rules to put down here. So I'm going to rub this out. Suppose I just put a constant here and x to a power here. And look at what it would look like if I wrote the definition of the derivative. That constant will be in front of both terms in the numerator. So that makes it a common factor. I can take the common factor and write it in front, and then the limit was a entity that allowed us to ignore constants and then take the limit of the good stuff. So that says I can pull the constant way out here and keep the limit on all the stuff that involved the h. But that was just the derivative of x to the n. And then I can take the derivative of it and then knock the constant back on. That's true in general, no matter what the function is. The derivative with respect to x of a constant times some function is that constant times the derivative of the function. So for instance, if I'm taking the derivative of something like this, (18 times x to the 3rd), I know the derivative of x to the 3rd. It's 3x squared. So the derivative of 18x to the 3rd, I almost said 18x to the turd. Beavis and Butthead. The derivative of 18x to the 3rd should be 18 times 3x squared. That's what that's saying. Okay. So your turn. What's the derivative of 6 times the square root of x? Just send it telepathically to me. Don't say it, just think it and send it to me. Here's what you're thinking. Oh, I can't write that. Who's thinking that? Saying I'm going to leave that 6 alone and bring the 1/2 down, 1 power less. And we just did this one. 1 power less than a half was a -1/2. Isn't that what you were thinking? Then 1/2 of 6 is 3. And we have that. We can take limits term by term. Suppose we had a bunch of functions added together. Well, a derivative is a limit, so we can take derivatives term by term. So the next one I'm going to add here is that the derivative with respect to x of f plus g is f prime plus g prime. And it works also with minus. The sum of the terms, the derivative of a sum is the sum of the derivatives. That was hard. Like if f of x, I think we did some version of this, 4x squared plus 6x minus 5. I have three things added together, but I know how to take the derivative of each of them. And that rule says I can take the derivative term by term, I can put the constants on the end, and I can take the derivative by bringing the power down and raising it to 1 power less. So I'm going to do that. Pull out the 4. For the derivative of x squared, bring the 2 down, 1 power less gives me x to the first. You can look at this as being the second rule, the mx plus b kind of thing. If I have those two terms together, that's just a linear portion, the derivative of that should just be the 6. And it is, because the derivative of x to the first power is 1, so I get 6 times 1. The derivative of any constant is 0. So there's our derivative, 8x plus 6. Okay. So let's go take that web work problem, web work number 5 up here. Let's do it together. Except for I forgot what it was. You still have it written down somewhere?
Yeah.
I'm ready for you.
F of x equals 6x to the negative 4th plus 5x to the negative 2nd.
We want to find
F prime of 2 and F prime of negative 3.
So let's find f prime at x. See if these guys can see it. Yep. So copy down to 6. Then take the derivative of x to the negative 4 by bringing the power down, raising it to 1 power less. Bring the 4 down, 1 power less. I'm going to write it so that you get the visual that I'm going down in power. Then the same thing with the other feller. Copy the 5 down. Bring the power down, raise it to 1 power less. So from now on, this is the part we're going to do in our head. I get paid by the number of steps, so I made another 15 cents by writing that down. So I'm going to put the constants together. 6 times negative 4 is negative 24. Negative 4 minus 1 puts me back to negative 5. And then here, 5 times negative 2 makes that a negative 10. And then x to the negative 3. Then remember that a negative power means I can put that term on the bottom and make the exponent positive. But only the x has the negative power. Those constants don't have the power on it. Writing it with positive exponents will help me evaluate it at numerical values. So I'm going to say that that's my derivative right there. And so the first thing I want is f prime at 2. Go in there and put a 2 in for each x. And we get that f prime at 2 is negative 24 over 2 to the 5th minus 10 over 2 cubed. 2 cubed is 8. 2 to the 5th is 32. So I have negative 24 over 32 minus 10 over 8. I suppose if we want to add those, I might want to reduce them. Each of those is divisible by 8. Yep. 3 times 8 is 24. 4 times 8 is 32. So I can write that as a negative 3/4. I can write that as a minus 5/4 for a grand total of minus 8/4. So that's the first one. F prime of 2 is a negative 8/4. Go further. That's a negative 2, isn't it? f prime of -3, let's bring it up here. F prime of -3 is -24 over -3 to the 5th minus 10 over -3 cubed. All right, -3 cubed is a -27. So if I take a -27 and multiply it by another -3, that makes a positive 81 times another -3 makes a negative 243. -3 to the 5th is a -243. -3 cubed is a -27. And I'm going to cancel the negatives and write that as 24 over 243 plus 10 over 27, and I'm going to say the heck with it. WebWork will take that. Okay. One thing that does confuse WebWork sometimes is if you put a negative number to a power. So you might want to go one step further and tell WebWork that that's going to be a negative number. All right, let me write a few up here and I will do some more with you. So erase, erase, erase. I thought I had a handout. What did I do with it? There it is. There it is. There it is. Okay, so the other day I sent you through the mail a handout called Elementary Derivatives. Do you have that in your mail? I have a handful of them here if you want them. I want one. Oh my God, you want to share one? That's big black thumbprint on it. Yes, Chairman, I'll write them up here. We're gonna go through there and see how many of these we can take. You gotta share with me. Okay, I can see upside down. All right, so take the derivative of the first one. We'll work through our handout problems once I find my eraser. Using our derivative rules over here. I'm gonna move that over. Derivative of x to the n was n, x to the n minus 1. And the derivative of a constant times a function is the constant times the derivative of the function. And the derivative of sum is the sum of the derivatives. So the handout says find the first derivative or find the derivative. And we've got 4x to the 6 minus x to the 3rd plus 2x minus the square root of 3. All righty. One thing I want you to do is not just string out equal signs. The derivative is not the same as the function. The derivative is the slope of the function. So when you go to take the derivative, label it. So just label it as f prime of x. Now go through there term by term and take the derivative. I'll give you a chance to do that while I erase the board. I'll even put the second one up here. So, Didn't make it any cleaner, did it? Square root of x minus 2 over x cubed. All right, you ready to check your answer on that first one? All right, I'm gonna copy down the 4. Take the derivative of x to the 6 by bringing the power down, raise it to 1 power less. Next, I've got a minus sign. X cubed, bring the 3 down, 1 power less. The derivative of x to the first power is just 1, so the derivative of 2x is just 2. The square root of 3 is a constant, so its derivative is 0. Good? Then I can put this together and make that 24x to the 5th minus 3x squared plus 2. And we'll get to the point where we just go straight from here to here, bring that with multiply and put it together there. If the x has the square root sign on it, then start by writing that as x to the 1/2. If it has a cube root, what is a cube root in terms of an exponent?
Okay.
So in general, if you have the nth root of an x to the mth power, the number on the radical sign is a root, that's the denominator of the power. So here I'm going to start by writing the square root of x is x to the 1/2. Also, if you have x's in the denominator, move them upstairs and make their exponents negative. They all have to be upstairs, written as a number times x to a power. So I'm going to rewrite f, so I can't just string out an equal sign there. This is still f. It looks like x to the 1/2 minus 2 x to the negative 3. Now you take the derivative of each term using that power rule. Bring the power down, raise the x to 1 power less.
That was number 3.
That was number 3? Oh, that was number 3. Let's put number 2 up here. 1 over the square root of x. So like before, replace the square root sign with a power, and like before, write it upstairs with a negative power. And now you're ready to take the derivative. Radical signs become fractional exponents. Things in the denominator move up, and the powers change sign.
In the exam, do you want us to leave it in a particular form?
I really don't care about the simplifying on an exam, but we need to get to a point where we can evaluate these things at numerical values. So I'm always going to simplify just so that you get the practice, but I won't make you simplify. Maybe.
Yeah, I was just like, if I leave it x to the power of the negative 1/2, would that be okay?
Well, we haven't taken the derivative yet.
Or like whatever the derivative is.
So we bring the power down, raise it to 1 power less. What is 1 power less than 1/2? Negative 3 over 2, because I'm taking negative 1/2 minus 2 over 2. Give me a negative 3 over 2. But just like in that web word problem, if I want you to evaluate this at a particular number, that's easier to do if the exponent is positive. The negative power means it goes in the denominator. Instead of putting it in the denominator of 1/2, I'm going to put it in the denominator of the 1. Right? X goes downstairs there with the 2. So now if you wanted to find f prime at 4, you could. Let's do it. If this is f prime, what is the value of f prime of 4? In other words, what's 4 to the 3/2 power? It's 4 to the 3/2 power. It's going to be 8. That half means square root. Square root of 4 is 2. The 3 is a power on the 2. 2 cubed is 8. So 4 to the 3/2 is 8. We can do the square root first, then cube it and get 8. This is negative 1 over 2 times 8, or negative 1 over 16. So my question might be something like this. If f of x is 1 over the square root of x, write an equation of the tangent line at the point where x is 4. So you need a numerical value for the slope. Heck, let's just do that problem. Let's add a third part to this problem number 2. Write an equation of the tangent line to f of x is equal to 1 over the square root of x when x is 4. What's the equation of any line look like? Y is equal to mx plus b, right? Or if you're going to write the equation of a line, maybe you want y minus y1 is m times x minus x1. We just figured out m to be negative 1 over 16. X is given to us as 4. All you got to do is tell me what the y value is when x is 4. The square root of 4 is a half. And now we have the 3 parts that we need for the equation of the line. Y minus 1/2 is negative 1 over 16 times x minus 4. And you can put it in whatever form you want. I'll just leave it there. Okay, so that's why we need to know how to manipulate radical signs and work with exponents and things like that, so that we can come up with numerical values to put things into our point slope form if we're asked to write the equation of the tangent line. Okay, so thought back to number 3. We've rewritten it with fractional exponents for the radical sign and positive x to the power for the x in the denominator. Take the derivative of each term, bring the power down, raise it to 1 power less. You want to simplify a little bit, write it with positive exponents maybe. But again, that's f. Now that you're taking the derivative, let's label it as f prime. Bring the power down, 1 power less. So we've done this one 3 times already. I'm just going to jump and write negative 1/2. Here, I'm going to go ahead and put the numbers together. I'm going to take this negative 3, multiply it with the minus 2, and get a positive 6. What's 1 power less? Minus 4. And now let's write it with positive exponents. I can write this as 1 over 2 x to the 1/2 plus 6 over x to the 4th. And if you want to put a radical sign instead of the x to the 1/2, you can, but it's only on the x. Okay, again, you can leave it here for me. This is how you would simplify it if you wanted to simplify it. Okay, so now I got to derive 2 more rules for you. The derivative of a product is not the product of the derivatives. The derivative of a sum is the sum of the derivatives, but the derivative of a product is not the product of the derivatives. I have 2 functions of x divided. I can't just take the derivative of the top and divide it by the derivative of the bottom. Let me show you with some basic functions. Erase. Let's see. Let's take, so the derivative of a product is not the product of the derivatives. In other words, something like this. If f of x, let me just take just two x to the power terms. Let's take an x to the 5th times an x cubed. That simplifies to x to the 8th. And x to the 8th has as its derivative 8x to the 7th. But now look at the product of the derivatives. The derivative of x to the 5th is 5x to the 4th. The derivative of x to the 3rd power is 3x squared. If you multiply those together, you don't have a chance in Hades of getting 8x to the 7th. You get 15x to the 6th. So you can't take the derivative of each factor and then put them back together. We have a product rule for that. Same thing if you have a quotient. If f of x is x to the 5th over x cubed, that simplifies to x squared, and the derivative of x squared is 2x. But if I looked at the quotient of the derivatives, if I take the derivative of the top and divide it by the derivative of the bottom, the derivative of the top over the derivative of the bottom in this example would look like 5x to the 4th over 3x squared. I can't get the x squared out of that, but I get a 5/3 x squared, which is not that derivative. So we can only go term by term through a sum, not through a product or a quotient. Now, in order for you to see what that looks like, I'll have you watch this. Don't write this down because I'm going to go fast. I'm going to derive the product rule. Then you're going to believe me on the quotient rule. But in the absence of time, here is the derivation of product rule. I'm going to let f of x be a capital F times a capital S. That's going to stand for first times second. And so the derivative by the definition, time me, see how quickly I can do this. I'm going to write the definition in general. Now I'm going to apply it to capital F times capital S. It'll look like F of x plus h times S at x plus h minus capital F at x, capital S at x, all divided by h. But if we take the limit as h goes to 0, this becomes f of x times s of x. So the numerator is 0, the denominator is 0. I can't take the limit yet. So what I'm going to do is I'm going to add 0. Here's how I'm going to add 0 with my handy dandy red marker. I'm going to write this. So let's see, I'm going to That's how I'm going to add 0. I'm going to put it in, I'm going to take it back out, and I still have this there. That's divided by h. I subtract f of x plus h minus s of x, and then I add f of x plus h times s of x, and I did that so that if I can factor these by grouping, the first two terms have a common factor of capital F of x plus h. The second terms have a common factor of capital S of x. So I factor, and it looks like this. Pull out the common factor. Next batch, I got the plus sign from here. The common factor is capital S of x. The other factor is f at x plus h minus f at x. That whole fraction is divided by h, which means I can break it up into two fractions, this one over h and that one over h, because they have a common denominator. But in a product, I can choose to do this, put the h with that, put the h with that. The limit of the sum of two terms can be done term by term. As h goes to 0 here, this goes to capital F of x. Do you recognize the parentheses around here? S at x plus h minus s at x divided by h as h goes to 0. What's that called? That's the derivative of s, right? So this stuff in these parentheses is s prime at x. That's s. There's the definition of capital F at x. And so here's the product rule. It's h goes to 0, so it's just the first factor times the derivative of the second factor plus the second factor times the derivative of the first. That's the product rule. First times the derivative of the second plus the second times the derivative of the first. It's added, so it doesn't matter the order in which you do this. If you want to do this one first, copy down the second factor, multiply by the derivative of the first, and then add that, that didn't matter either. The order here doesn't matter. Just hold one, take the derivative of the other. Then go the other way, add them together. I'm going to show you that it works on this one. And then you're going to believe me and work the one on the sheet. Okay, so we're going to look at it like this. And we're going to do the product rule, and we're going to come up with a derivative of x to the 8th. So by the product rule, f prime is the first factor times the derivative of the second. Derivative of x cubed is 3x to the second. Now add the derivatives done the other way. I copy down the second times the derivative of the first. Now I'm going to multiply those out. When you multiply like bases, you add exponents. So this becomes 3x to the 7th plus 5x to the 7th. Dun, 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 dun. That adds to 8x to the 7th, which is, by golly, the derivative of x to the 8th. Okay. Product rule. First times the derivative of the second plus the second times the derivative of the first. All right, so I think we got time to try the next one on the worksheet. Using the product rule. What number are we on? Number 4. Can you call that out to me?
It's h of t equals parentheses t to the third plus 3t to the second minus t plus 1/2, close parentheses, open parentheses, 4t minus 2. Close parentheses.
All right. So if you were forced to, you could multiply this out and get you about 8 terms added together and take the derivative term by term. But why would anybody want to do that when you have this handy dandy product rule? Copy down one of the factors, take the derivative of the other, do it the other way, and add them. You don't have to simplify, just leave it in product form. On your mark, get set, go. And this time t is the variable, so you're going to label it as h prime of t. Don't simplify your answer. We don't have time. Somebody took away a Friday class. I bet you showed up anyway, and you were looking for me. I was at the rec center with everybody else on campus. Those poor people couldn't get out of their apartments and dorms, but no, they could make it to the rec center. And that blizzard that we had of nearly an inch of snow. So there's the first, there's the second, and h prime is the first times the derivative second, second times the derivative first. Now I'm ready to do it. First, just copy it down, t cubed, 3t squared, minus t plus 1/2. Somebody call out for me the derivative of the second. 4, and that's all, right? Now go the other way, copy the 4t minus 2, and let's take the derivative of those 4 terms. T to the third, bring the 3 down, 1 power less gives me 3t squared. Now I plus, I've got a 3t squared as the second term, 2 times 3 gives me 6, 1 power less gives me t. What's the derivative of the minus t? Okay, and what's the derivative of the half?
0.
And then we're done. Okay, no need to multiply it out. All right, let's do the next one. No need to multiply it out, let's do it with the product rule. We've got 5x plus 1 times the square root of x. So really, the only thing you need to do is rewrite the square root of x as x to the 1/2. And now do that with the product rule. There's my first, there's the second. The product rule is first times the derivative of the second, second times the derivative of the first. So we have 5x plus 1. And now for x to the 1/2, you bring the power down, raise it to 1 power less. Now the other way, copy down the x to the 1/2. Derivative of 5x plus 1 is just 5. Good. If you did want to simplify, here's how you can do it. That's an x to the 1/2 on the bottom, which is a square root of x, and that's a 5 times the square root of x. Is that one prettier if you need to evaluate that at a certain point? And then I got a problem on the back page, ask you where some version of this is equal to 0. So it's nice to be able to write that in the denominator with this 2, goes underneath the 5x plus 1 only. Square root of x is the same as x to the 1/2. Okay, next we have a quotient rule. Derivative with respect to the x of the top over a bottom, where those are functions of x. And I can do the same thing. I can derive it using the definition of the derivative. I do the same manipulation where I add 0 by subtracting something, adding something gives me common factors. Almost the same exact steps. I'm just going to give you the formula for this. The derivative of a quotient is the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. This one, the order is important because of the minus sign in there. The derivatives have to be done in that order. Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Let's go back to our x to the 8th, where we wrote that. I'm sorry, not x to the 8th. Let's put an x to the 8th here and an x cubed there. That would simplify to x to the 5th. And the derivative of x to the 5th is 5x to the 4th. But I'm writing it like this. We're going to do the quotient rule and show you that this does indeed give you 5x to the 4th for you non-believers out there. Bottom times the derivative of the top will look like x cubed times 8x to the 7th. Agree? Now minus the other way. Top times the derivative of the bottom, 3x squared, all over the bottom squared. Now I know when you multiply like bases, you add exponents. What do I do with the exponents down there on the bottom? What is x cubed squared? Multiply, right? So this is an x to the 6th, and these are going to be an x to the 10th. So I have 8x to the 10 minus 3x to the 10 over x to the 6. So I have 5x to the 10 over x to the 6. Then here we subtract exponents. So we get 5x to the 4th. Isn't that what we said we were going to get if we simplified that first? It's not amazing. It's the quotient rule. And that's how you take the derivative of anything that's stacked up like a fraction like that. So I think we got time to do a couple more. Maybe one more. Depends on how slow you guys go. We have 5x plus 1 all over x. I'm going to show you two different ways to do it. One way is, of course, with the quotient rule. But if you just have a single term in the denominator, you can break this up into two separate fractions. And you can avoid the quotient rule. I can write that as 5x over x plus 1 over x. And then I can write that as 5 plus x to the negative 1. Then it's real quick to take the derivative. I just have two terms added together. So if you have a single variable in the bottom, you can break it up into two fractions, take the derivative of each term in the fraction, and we're done. Right? Now let's use the quotient rule, just because we have it. So this is one way. Simplify using algebra. Other option, you can use the quotient rule. So I'm back here in these parentheses. Let me copy it down. All right, so here's the quotient rule. Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Copy down the bottom, that's just the x. The derivative of the top is what? Your turn, play with me. Now minus the top. And your turn again, derivative of the bottom. Oh, 1. Derivative of x to the first power is 1. Bottom squared is x squared. Let's see how far that simplifies. Better simplify to a -1/x², or we're in trouble. That I can write as 5x, multiplied by 1 just gives me that term, distribute the minus sign. And there we get the same thing. Okay. Annie, how you feel? Good, practice them, practice them. Are you feeling the test on Friday, or would you feel better with the test on Monday? Either way, the test would go up to section 3.2, which is this stuff.
Monday.
Unanimous on Monday? Would that throw anybody into a loop?
No.
Okay, your
Will Friday be like a review day?
Friday will be review day. I've got a review sheet on the web work, but let's go ahead and move exam 1. Section 3.2 to be Monday. Is that? That's Valentine's Day. So I'm not gonna buy you any candy because I'm giving you a test instead. That's straight from my heart.
Thank you.
Thank you.
We'll practice these Wednesday. We'll review on Friday, test on Monday. That good, everybody home? Watch your steps, watch your steps.
Yeah, I'll take it. Whatever.
Monday, okay. But I need you guys here on Monday. Put fingerprints on it. It looks like a mechanic, don't they? Thank you.